My name is Costas Soukoulis, and I'm a professor of physics at Iowa State University, and I am a member of Ames laboratory. And also I collaborate a lot with the University of Crete in the material science department, and also with the Institute of Electronic Structure and Laser at Forth. And I'm doing a lot of work on photonic crystals and metamaterials. In the metamaterials, you can really do, this is the whole spectrum. You can do basic physics and applied physics, and it's the whole spectrum. So you can do simulations, theory, experiments, and so on. So we have all these kind of capabilities. And if you go in an area, you might really very narrow. In this particular thing, you can really work in any area that you like. Metamaterials, there are artificial materials that they have properties that they don't exist in nature. So you can really take a metal and a dielectric, and then you can really fabricate and to make a metamaterial, and their properties is completely different from the metal and the dielectric. And the metamaterials, they have very important properties. They have negative index of refraction, which doesn't exist in natural materials. I mean, the group and the phase velocity is positive. And of course, you can use the metamaterials because of the negative refraction. You can make flat lenses, which is very, very, very important idea. And also because the negative index of refraction, you can really make a super lens. So super lens really means, I mean, if you have some kind of lens, you can distinguish the distance equal to the wavelength. And then if you have a super lens, you can distinguish even tiny distance of the order of 10 nanometers. So really this is a holy grail of the metamaterials that we can really find out if we have the perfect lens, that we can really see molecules and DNA molecules, and we can really see all the small details. And that's one of the holy grails of the metamaterials. Nature does not give us optical magnetism. As Landau says in his book, if you go to optical wavelengths, mu, which is the magnetic permeability, is equal to 1. But once we have these metamaterials, which is really the split ring resonators and all these metamolecules, we are going to push to have negative mu at optical wavelengths. And in that way, we are going to really study optics with nonlinearity with the magnetic field component. So most of the nonlinearity that is happening in optics, it comes with the electric field. So you put an electric field, you apply a laser. Laser has both the epsilon, the electric field, and the magnetic field, and you excite only the electric field and you get nonlinear effects. But if you have a negative M, which is optical magnetism, it's open a lot of possibilities to study half of the optical field that we haven't studied. So far, I mean, the whole community, they have created really super lattices. They work only for one particular direction. And of course, we wanted to go to optics. And of course, as we go to optics in very, very small structures, I mean, the metals, they have a lot of losses. And one of the challenges is to reduce the losses. So really, in order to reduce the losses, you have to introduce gain. So one of the whole community is trying to do, they try to have quantum dots, which is they have a lot of gain, and you can excite them optically and electrically. And this can really be a very good idea to do it. Half of the community, they are using dyes, which lasts for a few minutes. And you can compensate the losses, but is useless. And another thing is another challenge is we try really to have three-dimensional metamaterials. And one of the things that we are doing in Ames laboratory together with University of Karlsruhe, we try to do direct laser writing. I mean, we have done these metamaterials in 3D at 3 microns, but we wanted to push it in optics. And also, another very challenging thing is to really convince the whole community that is coming from chemistry and biology to really start for bottom up. So if they have some DNA molecules, or if they have some kind of polymers, self-assembly polymers, so they can start from there up and they will go to the optics. So really there are 2 ways. Top down, the whole community is doing. We are stuck before we go to optics. And really the chemistry and the organic chemists, they have to help us, and biologists, to come from bottom up, and we'll meet together, and the dream of metamaterials will be possible.